Okay, in this next piece of the chapter, we want to look at free body diagrams, Newton's third law, and how these all play together, and look at a lot of examples of how to draw a free body diagram. A free body diagram involves drawing the object you're looking at as a point. We draw the point at the center of mass of the object, and that point stands for the entire mass of the object. Then we draw all the forces as vectors, as arrows, in the correct direction, with length equal to their magnitude, so longer arrow means a larger magnitude, and labeled with the correct symbol for the force. So we're going to draw all the forces on an object, pointed in the correct direction, drawn to the correct length, all originating from the center of mass of the object. So this is a diagram that allows us to see all of the forces that are occurring on an object. To really understand this, though, we need to talk a little bit about Newton's third law. You started looking at Newton's third law today in your lab. Newton's third law deals with what happens when we have a force, built upon the ideas of the first and second law, and now looks at the interaction nature of forces. Newton's third law states that whenever one object exerts a force on a second object, the second object exerts a force equal in magnitude and opposite in direction on the first object. Many people summarize this third law: for every action there's an equal and opposite reaction. I think that is a little too simplified for what we are talking about. I think the easiest way to summarize this is for every force, there must be a force of the same type, equal value in the opposite direction. If you have force normal of A on B, you must then have force normal of B on A, same value, in the opposite direction. So while this phrase, for every action there's an equal and opposite reaction, is helpful, this does not give us the full details. So it's important that you understand the full details of what we're looking at. When we start to draw free body diagrams, understanding where these pairs of interactions are coming will be very important in helping us draw these diagrams. So let's look at a lot of examples of these diagrams. A book sliding across a table. So we're going to draw, we want to put a dot to stand for the mass of the book. Then we want to draw all the forces that are on the book. One force we know we're always going to have on Earth is the force of gravity, which will be pointed down towards the center of the Earth. The table is going to push up on the book. Two surfaces in contact, so I'm going to draw on a dashed line here so we see where the table is located. And this is our book sitting on our table. The table is going to push up perpendicular to the surface, table pushing up on the book. The pair to that in Newton's third law would be the book pushing down on the table, which would be in the free body diagram for the table. We know it's sliding. Let's assume it's going this direction. If it's going that direction, we're also going to have, parallel to the surface, the force of friction. And this will cause it to slow down and come to a stop. If it were a frictionless surface, we would leave that out. Okay, a book resting on a table. Once again, I'll draw on a dashed line for our table, our book. On a dot for the book, we're going to have gravity pointed down. The normal force of the book pushing up on the table, perpendicular to the surfaces that are touching this surface right here. In this case, it's not moving, so we're not going to have any friction. It's not trying to move. No friction. There's no spring, no rope, so no spring or tension forces. We don't include air resistance usually. It's not moving, so we wouldn't have any air resistance. So these will be the only two forces. The book is not accelerating, so these two will be equal in length, opposite in direction. Cancel each other out. A table with a block sliding across it. Try this one on your own, and then press play again once you've tried it to see what's going on. So I've got my block. I want force of gravity going down, force normal going up. I'm going to assume it's sliding in this direction. So friction always goes opposite of motion, parallel to the surface. So we'll have a force of friction there. Monkey hanging by a string. In this case, dot stands in for our monkey. Gravity going down. The string will be pulling up parallel to the string. That will be a tension force. A rocket launching. We have the force of gravity going down. In this case, we don't have a specific name. It's actually a thrust force. It's pushing gas out the bottom of the rocket, which the gas then pushes the rocket forwards. I will just refer to that as the force of the rocket. Since it's launching, this arrow here must be longer than the gravity going down, so it accelerates upwards. Spring with a mass resting on it. We'll have force of gravity down. And the spring pushing up equal to gravity because it's not accelerating. Now here we have a diagram with a lot of different objects on it, A through I. We're going to do the free body diagram for each of these, a number of these different objects. So we'll come back and look at this picture each time we do a free body diagram. The first one we want to do is D. The free body diagram for object D. So we see object D here. It's sitting on top of E. It's connected to a spring with F. The springs here are all stretched. We will assume all the springs are stretched and nothing is moving. Okay, so D, we've got the force of gravity going down. We've got the normal force from E pushing up. The spring is stretched, so it's going to pull back in towards the center of the spring. And what's keeping it from moving, therefore, must be friction. All these balance out, and the object is sitting still. Next one is B. So let's go back and look at our diagram. B is sitting here on the surface. It's touching A and C are the only things touching it. So I'll draw a little picture of this so we can see it, so we don't have to go back to the diagram to look at it. So B, C, sitting on top of it is A. Now this one's a little bit more complicated. We have gravity pushing down. It's touching C, so it must have a normal force perpendicular to the surface, pushing up. A, now remember, A is at an angle. A is pushing down perpendicular to the surface. So if this dashed line is the surface where they're in contact, perpendicular to that is where the normal force is going. And then if A is not sliding, there must be friction going that way. If B is exerting a frictional force on A must be exerting a frictional force on B, Newton's third law. So this one's a little bit more complicated case. Okay, let's look at G. Let's go back to our diagram. G has two ropes and a spring. So we'll think of it as a rope, G, our spring, and another rope pulling down. Make sure I have that right. Yes. Okay, so our free body diagram in this case, first one we always start out with, gravity pointing straight down. You have a rope pulling up, parallel to the rope, so a tension force that way. You have a tension force pulling down the other rope, and the spring is stretched, so it pulls towards the middle, so you have the spring pointed to the right. So when you're going through these free body diagrams, I highly recommend you think through the following steps. So the steps, I would always start force gravity. It's going to point down towards the center of the Earth. As long as we're on the Earth, we're going to have the force gravity. Is it touching an object? If it's touching an object, we're going to have a force normal. It's always perpendicular. That's a symbol for perpendicular to the surface. Perpendicular to the surface that's touching. Is it trying to move or moving? In which case we'll have friction parallel to the surface. That's the symbol for parallel here. And opposite the direction of motion. Is there a rope, string, force tension, parallel to the string? Is there a spring? That'll tell us there's force spring. Force spring will be towards the center if it's stretched, away from the center of the spring if it's compressed. So that's generally the questions I would go through when thinking about which forces to write. Know those forces, know which directions they go, so that you can clearly label them in the free body diagram. So here we have another one, C. C is going to be our most complicated one. C has I, B, E, and F on top of it. 4 strings pulling down. Now make sure understand this string here. This is not attached to anything. It's not tight, so we're not going to include it. So for C, we've got a string here, a spring here, I, B, E, and F all on top of it. We have 2 strings coming down this way and 2 strings coming down that way. So I'm going to start. I'm going to make a really big dot here so we can clearly see all the different forces. We're going to have the force of gravity going down. Next, are there any objects touching it? Well, we have the 4 objects touching, so I'm going to have 4 normal forces. All 4 of these are normal forces. I've got a spring, so I'm going to have a spring force. I've got a tension force from the 2 spring and string pulling up, and then I'll make my dot even bigger here. I've got a tension force going this way, a tension force going this way, and 2 tension forces going down. So this has a lot of different forces because it's touching 4 objects, has 5 strings attached, so 5 tension forces and 1 spring. So if you'll go through those steps, and we're going to practice this with a worksheet in class tomorrow, I think you'll start to pick up the concept of drawing free body diagrams. The key is understanding the different types of forces and labeling them all clearly.